Okay, it's my pleasure to introduce our last speaker of the day, Professor Amin Karbasi from Yale. His research spans many different areas, too many that I'm not going to list them here, but he's received many different awards from his work, including the NSF Career Award, the ONR Young Investigator Award, and similar awards from the Air Force Office of Scientific Research and the Defense Advanced Research Program Agency. Today, he's going to talk to us about replicability in interactive learning.
Okay, thank you very much for the introduction, and thank you for the invitation. Outside is beautiful, and thanks for sticking around. So I'm going to talk about a very, very simple problem that I've been thinking about in the maybe last year or 2 years, which is about responsible AI. And a few months ago, we actually had an executive order about how should we use safe, secure, trustworthy developments of the artificial intelligence. We are developing this kind of technology, but at the same time, we have to think about how we are using them and what is the right way to do. There are a lot of facets about responsible AI. It comes in many different ways. Like, we have to ensure fairness of the algorithm that we are designing, right? So they should not have preferences to some groups of people and not to the others. These algorithms have to be reliable. Like, if there are malicious users, they should be protected. They have to ensure the privacy of the users, and many, many, many other things. But maybe in the last year or so, I started thinking about responsible AI, step 0, and can we even trust the results of the machine learning algorithm that we are developing? If I run the algorithm on my computer and you run it on your computer and we get different results, then we cannot even trust them. The other questions that are very important and timely, they may not even be relevant if we cannot even trust that the algorithm is going to output something consistent, right? And this is a real problem, and there is a very, very nice Nature paper about, is there a reproducibility crisis? In general, in science. What they did was that they gathered like 1,500 researchers, and they took an online questionnaire about reproducibility, in their field of research, and more than half of the people said that there is a serious problem about reproducibility. Only around one third, think that reproducibility is actually that failure to reproduce published results means that the results are probably wrong. So why only one third of the people? Because there are a lot of things that are going under the hood. Maybe you cannot reproduce a result because the details have not been clearly explained in the papers, and we have written so many of those papers ourselves, right? But still, many believe that we can trust the published literature. Okay, so far so good. So then, what they did is that they asked people in different research groups how much they believe, how much confidence they have about their own field, right? The results of their own field. And here, the chemists and engineers had the highest confidence because we use very rigorous methods, we experiment, we take our time, right? And then it goes down to in medicine, you see all the results that they flip-flop over time. But then they did something super interesting. They asked people in, in each group to reproduce the result of another person in their field. All right? And here, suddenly the chemists are the worst. 90%, almost 90% of the time, they couldn't reproduce the result of another group in chemistry. And what was even more interesting to me was that when they asked people to reproduce their own result, 50% of the time they couldn't. So I think that is a problem. And then I thought, I'm probably better. I can reproduce my own results, but then, you go back to a code that you wrote 2 years ago, run it, and it doesn't work, right? And maybe, people here are better, and maybe students in BU are better than the students that we have. But I guess if you ask them to reproduce the result they had 2-3 years ago, the chances are they cannot, or half the time they couldn't. So this is a problem that has been highlighted in the AI community, because it is one thing that we have like reproducibility crisis in science. It's another thing that we have this magic box of AI. We don't know exactly how it works. We combine it with science, and we produce new science. So it's suddenly the problem is, on steroid. And there are a lot of discussions in the AI community, how much we can trust such results. And especially these days, we don't know exactly how the models work. We don't even have access to the data. But then a group of researchers claim a result. Yes?
So the term I cannot reproduce is kind of vague.
Yeah, I have to.
Clarify what it means.
Yeah.
Have access to the same data, same code, and maybe the version of the code that was running at the time, maybe the story will be different.
Yeah, I completely agree. And that is my try today, to actually make it a little bit more rigorous, what we're talking about. And I'm not going to say that this is the only way to talk about these things. It's one way to talk about it. But I completely agree with you. So how does it work? How we actually solve the reproducibility crisis these days? Well, there is we cannot reproduce a result. There is a bug. We try to come up with the fix, and then suddenly there are many more. Why? Because what you see here on the on top, this is the number of papers at NeurIPS, and we are getting to the point that it is going to be vertical, so infinitely many papers a year. Is it possible to reproduce the result? Probably not. It's very hard. Right? So, and the way that I would like to think about this problem is that, can we guarantee reproducibility or replicability of the result in an algorithmic fashion from the get-go, from the beginning? We think about reproducibility. We try to design an algorithm that we can guarantee it's going to reproduce its results. All right? So we are going to take an orthogonal path, and we are going to think about algorithms that we are designing with the guarantee that they should be reproducible. So technically, what I'm going to talk about, there are many different terms, in regards to the question that was asked. There are terms like reproducibility, replicability, robustness, and generalization. In particular, today, I'm going to talk about replicability. And that means redoing an experiment with different data that is sampled from the same distribution, but using the same analytical tools. Okay? So pictorially, what we are trying to do is as follows. We have a hypothesis, and then there are two groups of people. They collect their own data, and for now, we are going to assume that the data are sample IID from the same distribution. The two data sets are completely different, presumably, but they are sampled from the same distribution. They are going to use the same kind of analysis. When I say the same kind of analysis, what I also mean is that they're going to, if the algorithms are randomized, they're going to use exactly the same randomness. If you're using SGD, you share what random bits you're using, what randomness you're using, and give it to the other group. Both groups are going to use exactly the same random bits. So what is different is the data. And what you would like to get to is the same conclusion. So mathematically, this is what we are trying to achieve. So we say that, so D is an unknown distribution over a universe X, and we let A to be a randomized algorithm that can sample IID from this distribution D. We say that the algorithm A is row replicable, means that with probability 1 minus rho, with high probability, the output of A, given the data set S, with the randomness R, is going to be exactly the output of A, given the distribution, given the data S prime, sampled from the same distribution, and the same random bits. So that was the notion that was proposed by Russell, Rex, Tony, and Jessica. And what they wanted to understand is that, can we achieve reproducibility, replicability under this notion? Yes?
I guess the way most people think of this is more like for the same answer, you can exactly but slightly
Right. So that is why. So replicability, in this category of algorithms are like the same algorithm, two different data sets, but samples from the same distribution. What couples the executions is that they sample the data from the same distribution. So like in clustering, a group of people, they want to cluster the data. They say that this is how it works. And then another group, they have pretty much the same kind of data on patients. They cluster. They want to make sure that they get to the same cluster centers. All right. So the best way to understand this definition is to try to actually, look at an example. For instance, let's say that I want to estimate the mean of a distribution. There are two groups. They can sample data from the same distributions, but the data points are very different. Is it possible to guarantee, is it possible to come up with an algorithm that guarantees that the results are going to be exactly the same with high probability? There is a trivial answer to that. If you don't care about the mean, you don't look at the data, you always say 0, right? So you can always come up with such an algorithm. It just, it's an algorithm that doesn't even look at the data. It always says 0. It is definitely replicable with this definition. So what makes a problem interesting is that you want to be epsilon close to the actual mean of the distribution. So what you're going to do is the simplest kind of idea. You discretize the domain into boxes of size epsilon. You sample enough data points so that by concentration bounds, both estimates, the empirical estimates, are going to be in the same box. And what you do now is that you collapse your estimate to one of the two endpoints. Right? This is almost a solution, but there is a problem. If the mean, this has to work for any distribution, in particular, if the mean is in the middle of the box, then one group is going to underestimate, the other group is going to overestimate with constant probability. All right? So what you need to do is also to add a random shift and share it with the two groups. Once you do that, then it works. And what is very curious about this solution is that in order to achieve replicability, in order to get to the same result, we had to use a randomized algorithm. We had to add randomness. Without randomness, it is impossible to achieve. And what Russell and company showed that for any statistical query, the number of samples that you need is going to scale like 1/epsilon², and 1/rho², if you want to get with probability 1 minus delta. Okay, so almost everything in this result is typed. And this is going to be the building block of what we are going to do today. So any statistical query with this rounding technique and random shift, you can make it replicable with high probability. But today I want to talk about replicability in the context of interactive learning, in particular like reinforcement learning. Okay? And when we have agents, these are my kids, I ask them to draw racing cars. They try to replicate from one another. The results are maybe similar, but quite different. And what is, for anyone who has kids, what is hard actually to consider is that I'm not even sure that they have a policy in mind, or definitely it's not time invariant. So they randomly change their policy. So I'm not going to talk about these real agents. I'm going to talk about much simpler problems that I can mathematically discuss. So let's start with the simplest kind of interactive setting. A stochastic bandit. We have a horizon T. We have it's a stochastic setting. So each arm I has mean mu I. And the problem that we would like to understand is which arm to pull in every iteration in order to minimize regret. And throughout the day, we have seen there are many, many different algorithms in the literature, including UCB and Thompson sampling. But can we do that in a replicable manner? So what does it mean in a replicable manner? It means that for time horizon T with k different stochastic arms and replicability parameter rho, we say that the bandit algorithm is rho replicable if it with probability 1 minus rho, it pulls exactly the same sequence of arms across two different executions. All right? So there are going to be different realization of the words across executions, but what we can do is that we can share randomness between the two executions. And what we would like to understand, which is a little bit counterintuitive, is that how we can trade off between replicability and regret. So all the algorithms that we know about in the bandit settings, they rely on this randomized exploration and exploitation, right? Somehow what we are trying to do is the opposite. What we want to come up with is that an algorithm that, if you run it in this environment, it selects a sequence of arms, and it guarantees that if you rerun again in an independent environment, it's going to select exactly the same arms, but it's going to minimize the regret, which is a little bit in the opposite direction of bandit algorithms. So what we can show in this setting is that, for the stochastic bandit setting, the regret is if you have a suboptimality gap delta, then the regret is going to scale like log t over rho squared delta. So log t over delta is optimum. rho squared is also optimum, so we can show that all these terms are optimum. The only thing that is not optimum is actually, the blow-up k-squared compared to the non-replicable case. All right, so if you guys can come up with a solution, we'll be happy to add it to our slides. Okay. And we can extend this to the linear bandits. So what is the idea? Well, the idea is based on batch bandit literature. So what are we going to do is that we are going to divide the bandit setting into the arms into two sets: the active set of arms and the inactive set of arms. And initially, all the arms are going to be active. Then, instead of being fully sequential, what we are going to have is we are going to divide the horizon into different epochs, into log t epochs, okay? And the length of each epoch, I, is going to be twice the length of the previous epoch. That is why we are going to have log t. So within each epoch, what we do is a deterministic round-robin fashion. Okay, so nothing here is going to be stochastic. And then what we do is that we estimate the reward of each active arm using the replicable analysis that we had for the that we just talked about in estimating the mean or any statistical query. And if we see that an arm, its reward is below certain threshold, then we are going to remove it. So these are going to be the deactivated arms. And once you do a naive analysis, what you're going to get is actually a blow-up of log t squared, because you have to make it reunion bound over log t batches. But what is important is that we can avoid such a union bound, because what we can do is that based on the offset, we can divide the arms into three sets. So you're going to be, no matter what the offset is, these arms are not going to be eliminated. For some offsets, an arm is going to be eliminated, or for all offsets, it is going to be eliminated. And the most important insight is that an active arm can remain in the uncertain region, this gray region, only a constant number of epochs. And that means that the union bound should not be over log t epochs, it should be over a constant number of epochs. And that is why we can get rid of this log t squared. Okay? Good. So now that we understand how to do replicable bandit, we can say, well, how about, a replicable RL? And literally what happened was that two groups of people theoretically replicated each other's result. So these two papers came maybe 2 days apart from each other on arXiv with basically the same result. So, what is a setting? We're going to consider the tabular MDP setting. We have a state space S. We have action space A, the discount factor gamma, and the reward function from state and action to 0, 1, and the unknown stochastic transition matrix. The policy is nothing but from state to action. It's a randomized mapping. And then the goal is to maximize the reward, or discounted reward in this case. And what we are going to consider is the simplest kind of RL setting where we have the generative model, which means that the learner can get samples from P for any state action pair. And our goal is to understand how many samples we need in order to find an epsilon optimal policy. Okay. So what is replicable RL? In this setting, for a fixed tabular MDP and a replicable parameter rho, we say that an algorithm that draws sample from the generator and internal randomness from R is going to output a policy. So the output of the algorithm is a policy. And what we want is that with high probability, over two sets of data, so it's an offline setting, S and S prime, that you sample from the generator, we want to get to exactly the same policy. So the main challenge here is that different executions observe different transitions. And of course, we have to trade off between achieving high expected reward and being replicable in this setting. So what is the roadmap? How can we achieve the same policy under two executions? So what we can show in the tabular MDP is that the number of samples in order to find a row replicable algorithm that outputs an optimal epsilon optimal policy is going to scale cubic with the number of states and actions. So there is going to be a huge blow up in terms of the state and actions. As I said, the same result was independently obtained by Ethon and company. And of course, an important question is, can we avoid it? So the roadmap is as follows. What we are going to do is, what we would like to do is to estimate the Q function in a replicable manner. Because from the Q function, the Q function is a function of a state and action. From the Q function, it is easy to go to a policy. Okay? And there is a very important and old result that says that if you estimate the Q function well, meaning with epsilon error, then the greedy policy is going to be the epsilon optimal Q function is going to be basically epsilon over 1 over gamma optimal policy. So what are we going to do? We're going to combine the traditional Q estimation with the replicable statistical query estimation. How many samples the traditional Q estimation requires? This is the number of samples, without replicability. And in order to guarantee replicability of a single pair, we need to blow up this number of samples by 1 over rho squared. And using the union bound is going to get us the result. Okay? Good. So now, at least, with this notion of replicability, it's going to be a huge blow up in terms of the number of samples that we need to get. So is it possible to actually consider a different notion of replicability and get better results? So if you remember, the way that we talked about replicability, and maybe it's related to one of the questions, is that we assumed that the two algorithms are going to share the randomness, right? And we wanted to get to exactly the same result. So we wanted to get, if we wanted to estimate the mean of a distribution, we want to get exactly the same mean. But maybe what we really want is that one group runs their own algorithm, the other group, and they get to some conclusion, another group are going to use pretty much the same algorithm, but with their own random bits, right? The groups are not even going to share the randomness between themselves. They both know that they're going to use SGD, but not exactly the same random bits of SGD. And they want to get to the similar conclusion, not exactly the same conclusion. So how can we define such notion of replicability? This is what we, in another paper, we call it a statistical indistinguishability of learning algorithms. So we say, if D is a statistical dissimilarity measure, we say that a learning algorithm A is rho indistinguishable with respect to the dissimilarity measure D if for any distribution over any distribution D over inputs and two independent sets of data S and S prime, if we look at the expected dissimilarity measure between the outputs, they are going to be very close. They are going to be X and rho. So here there is no shared random bits between the two runs of the algorithm. It's only the algorithm A that gets S and another one that gets S prime. And we take the expectation over all the randomness indices. Okay? So it's an information theoretic way of looking at replicability. And basically we are looking at the distribution of the outcomes of learning rules being indistinguishable under resampling. So now let's define, be very specific. We can define many dissimilarity measure, and one dissimilarity measure is like the total variation. So if we take, D to be the total variation, it is basically the best coupling between, the total variation between distribution P and distribution Q is, the best coupling of two random variables X and Y, where X, the law of X is P, the law of Y is Q. And, we say that it, if we take, the TV distance as the dissimilarity measure, then for a fixed tabular MDP environment and a parameter P, we say the algorithm is going to be rho TV indistinguishable if the expected TV distance is going to be less than rho of the outputs. Okay? So why the TV distance is the right notion? Because if the TV distance is small, then there is no statistical test that distinguishes the output of the algorithms. Statistically, you cannot distinguish whether the output comes from the first or the second group. And it is easy to see that, replicability implies TV indistinguishability, and I'm going to talk about it. But what is very surprising is that TV indistinguishability, which is about the best coupling, also implies replicability. But this transformation requires exponential time. Replicability is efficiently testable, but TV indistinguishability is not. However, replicability depends on how we share the random bits, and TV indistinguishability does not. So how is it like, one of the main results that I was confused for some time was how, these two notions. One, replicability is such a very strong notion, and TV indistinguishability that seems to be a complete relaxation of that notion are basically the same. One way is easy, from, if you look at replicability, it's a particular coupling. We couple the two executions because we share random bits. So of course, the best coupling is going to be smaller, and that means that, TV indistinguishability is going, if, replicability is less than rho, TV indistinguishability is going to be less than rho. But the other direction is much more complicated. You have two runs of the algorithm. You know that in terms of the TV distance, they are close, but these two runs, they have no communication between themselves. Is it possible actually to you know, is it possible that they output something very similar by shared random bits? And it turns out that you can do it, and the idea relies on the generalization of the von Neumann rejection sampling. So if A of S is the output of one algorithm, it's a distribution, A of S prime is another distribution, then what you can do is basically the shared random bits is going to be a Poisson point process. And what you do is that you sample from this Poisson point process. If it is below the PDF, you accept it. If it is above the PDF, you don't accept it. And the probability that you're going to sample two different points, that you accept two different points, is going to be related to the TV distance. And this is not our result. This is a result by this paper that is not, maybe it's been cited 10 times or something, but it is a super amazing paper. So and what in this paper they show is that everything on the right-hand side is optimum. That's the best you can actually get through shared random bits, through shared randomness. Okay, so if we use TV indistinguishability, then we can actually, as the notion of, as a relaxation of the notion, then suddenly we can get better results, even though statistically they're equivalent in the number of, the number of samples that you require in order to output two policies that you cannot statistically distinguish between them is, you're going to improve by, S times A. But it requires exponential time because we are going to use, the reduction from TV indistinguishability to replicability is going to be exponential. And it is generic. So if you give me an algorithm, I can actually turn it into a TV indistinguishable algorithm. So any algorithm you come up with whatever sample complexity, we can turn it into an algorithm that is TV indistinguishable. The idea is very similar. Up to this point, it's all about, Q estimation with, TV indistinguishable statistical query estimation. The difference comes when, when we want to couple the two executions. What we are going to do is that we are going to add exponential noise. This idea, which is a super nice idea, comes from the differential privacy community. So instead of sharing random bits between every pair of S and A, what we are going to do is that we are going to couple them using an exponential distribution. And then we can show that by doing this, the TV distance is going to scale with the square root of the number of states and action instead of the number of state and actions. Okay. So now, is it possible to get even better results? So what we can do now is that can we consider even a more relaxed notion of replicability? And this is what we call the approximate replicability, which means that the outputs, the two policies might be very different. But if you look at the output, okay, the distribution of the output, they are going to be close for any state. And if you use this as, our notion of approximate replicability, now, they don't have to be exactly the same, right? They shouldn't differ too much from one another. Then, which means that for every state, the distribution over actions are close, then we get even better results in terms of it's going to scale the number of states and actions. So far, I only talked about, the generative model, but, Eric, the other paper that I talked to you about, they extended the results to the episodic setting. And, if you have H episodes, in the reinforcement learning setting, then they can basically show a replicable algorithm where the number of samples is going to blow up, right? And the way that they do it is that, they have to come up with in the episodic setting, there is a very famous algorithm called Rmax. So the non-replicable version, the number of samples is going to scale like this. But what is a challenge is that, they want it to be replicable. So they have to make sure that, they visit every state action pair sufficiently many times so that, they can apply the replicable SQL estimate. Good. So that was a tour de France of, replicability in the interactive setting. We discussed different notions of replicability. There are so many open problems now. Any talk that you saw today, you can ask the question, can you make it replicable, right? So can you actually go beyond, for instance, tabular setting? Can you go to the online setting? Can you improve on the sample complexity, right? For the exact replicable notion or the TV indistinguishability, or there are other notions of replicability that you can think of. So when we posted, we posted the paper and then we talked, we put it on Twitter, here, Andrea said that, in regards to improvement, have you tried turning it off and on again, right? And of course, Casper came up with that this always works. But if you have better solutions in order to improve the sample complexity of replicable algorithms, then I'm all ears. And with that, thank you very much.
Thank you. Thank you. Do we have any questions from the audience? Yeah.
Does something like this TV indistinguishability to replicability reduction hold for the bandit setting, and can you hope to use that to pull down the K-cubed?
Can I?
Or do you think it might be possible to do that?
Yeah. I don't know how.
Okay. Oh, so that reduction, you don't know if that works for the bandit setting.
So you can work it out for the bandit setting. What I'm saying, I don't know whether. Okay, so I see what you're saying. So from K cubed to K squared, that can be done.
Okay.
Yeah.
But it's still inefficient at K squared.
It is. Yeah, it's going to be exponential time. Yes. We don't know how to get around this exponential time. And this comes because of this von Neumann rejection sampling, because you may need infinitely many samples to reject. And that's very inefficient. And we don't know of any other method.